These are the questions from carboxylic acids and amines. So first reaction being this one, where you have heat to be done with two COH groups present. See, once you fix one COH groups, the next carbon is alpha, after that is beta. So this is a beta dicarboxylic acids. And you know that in beta dicarboxylic acid, here, when it comes to uh, beta dicarboxylic acid, you will notice that one COOH will completely go away. Okay, one COH will completely go away, leaving behind only hydrogen there. So that's why you will see COOH will come here, H will come here, CH3 will come here, H and D will come here, C2Hy will be present here. Now this is interesting that this either I can take this COH or I can take this COH, right? So one time COH can be on the right hand side, the other time the same COOH could be on the left hand side, like this. But is there anything different that is happening on the lower carbon? Nothing, because lower carbon is not at all involved into any reaction here. That will remain the same. So can I say that these two are the products? Okay, decarboxylation will happen, carbon dioxide will go away, and these two are the products. Now have you noticed that the chirality of this chiral center is the same? I mean, the configuration of these two chiral centers is same, but the configuration of these two chiral centers is different, which means if this is, let's say, R and S, then this will become S and S. Is that clear? So if this is R, now this will become S, but this will remain S and S. So what are these two? Dash stereomeric pairs, because they are not mirror images, but they are stereoisomers of each other. So hence it is P. So dash stereomers of each other. Clear, beta? Same way. Here also I can do the same thing here. So I can get H here, COOH here, CH3 here, and phenyl here. Likewise, I can have acid with hydrogen here, CH3 here, and pH here. So what are we getting? 50% of this and 50% of these are the chances. This is what I'll get. Single chiral center, both of them are mirror images of each other. What are these two? Enantiomers. Okay. And 50% of each of enantiomer will make it racemic mixture. Clear?
Yes,
And here also CO2 gas is evolved. In the first case also CO2 gas is evolved. So S will be there for both the options. Third one, check out. Here same logic will be applied here. The lower methyl has nothing to be disturbed, but the above one decarboxylation will happen. Once you can get a product this way, or one product will be other COH remaining in this way. So what are these two? These are cis and trans isomers. So you can see this is cis and this is trans isomers. Cis and trans isomers are nothing but diastereomers. So here also we have diastereomers, and here also we have gas released. Next one. In case if at all I have a alpha, beta, gamma. So in case of gamma position, then dehydration will only take place, and you will get an anhydride formation here, like this. Water will come out and dehydration takes place and anhydride will form. Okay. And as it forms anhydride, can you see these two are chiral centers? But across this chiral center, there is a plane of symmetry running through it, isn't it? Across these two chiral centers. So a molecule is stereoisomer, but it has uh, optical inactivity due to a plane of symmetry. What do we call it? We call it as a mesoform. So there is only R. There is no carbon dioxide released here. So it is only R. So these are the options you need to check. Okay with the question? Any doubt?
mm,
Hmm. Let's see the next one. What will be the compounds which are oxidized by HiO4? Okay, see, to remind you, HiO4 basically helps in aldehyde and alcohol present adjacent to each other. Okay, So let's say here I have two carbons, correct? One is double bond O, the other one is OH. Here also HiO4 will help in breaking the bond. Even if you have two OH groups also, it will help in breaking the bond. Even if you have one NH2 and one OH also, it will break the bond. Even if you have two NH2 also, it will break the bond. Like this, it will break the bond. Even if you have two keto groups like this, two aldehydes or two keto groups also, it will break the bond this way. Okay, clear beta? So all you need to know is that we should have a vicinal position of OH and another group could be NH2 or aldehyde or a ketone like that. Then you have to break it. And remember, I told you about this in alcohols. Whenever you break it, one OH should be always given up and one OH should be given down. Going with that logic, here we have CH, then double bond O connected with C double bond O CH3. Now, as I break here, I will be giving one OH above and one OH below. The above COOH, C double bond O, and one more OH will come. So that will make it HCOOH. So what is that becomes? Carboxylic acid. The bottom one will also become CH3. C double bond O is already existing. One more OH is coming. So what do I get? I'll get formic acid and acetic acid. So which is answer? S. Clear?
Yes, sir.
Next, we have cyclohexane one dione. Okay, 1,2-dione. Same logic here also. You have like this double bond O and double bond O. So again, you break it here. So you will get, acid COOH, and then we have CH2 of four groups, and then again COOH. So six carbon acid. Six carbon acid is called adipic acid, and this is R. Adipic acid has been given. Next, here we have, you know, H, HC double bond O, HC double bond O connected with CH and PH double bond O. So as I break it here, I have up we will have HCOOH, down we will have PH, you know, uh, sorry, here there is no H. PH, no, sorry, there is OH here, my mistake. H and OH here. So there are two OH groups. Two OH groups will make it ketone. So these are the products you will get. So you can see formic acid, and you will have no, there is one hydrogen here. So that makes it benzaldehyde. So which is the case here? P. Last one. We have CH3 here with C double bond O connected with next CH OH here and ethyl here. So as it breaks here, so we will get upside we will get CH3COOH and outside we'll get EtCOOH. Sorry, EtCHO. EtCHO. So propanol. So which is that case? Q. Else clear beta. Please do ask if you have any doubt in that.
Sir, if we're adding a OH to the second part also, then won't it kind of
We will have two OH, na beta, here. One OH is already there. You will give one more OH. So two OH will convert into an aldehyde. Hmm? If you have three OH groups, it will convert into an acid. Clear,
but
clear beta.
yeah.
Let's see the next one. Suppose I have this group here and I make a reaction. What is the product I can get? See, nitrogen is a better supporter to C double bond O compared to oxygen. So definitely you can expect this to attack here. This bond will open here. So that's how you can get an amide form, C double bond O, NH methyl group, and this will be connected as C double bond O, O minus. Okay, O minus as in OH will be there here. Clear? So what is that compound? S. Similarly, nitrogen from here will connect on C double bond O, removing out chlorine. So we can have C6H5, C6H5 as in benzene, benzene connected with C double bond O, N and methyl group. Okay, so which is R. Next one. Lone pair from here attacks on this position, so that leads to PHC double bond O. Sorry, not double bond O, addition here. So we will get this as O minus. Okay, O minus H with NH and pH. NH and pH. Clear? So this is NH2 plus we got. So O minus can take away H plus and you'll get this as pH CHOH with NH and pH. Now the heating part is missing here. Only when you heat it, you will get this as CH double bond N and pH. Okay, imines will form. So which is option P. Okay. And lastly, lone pair of nitrogen can attack on sulfur, remove this chlorine, and you'll get sulfamide, which is option Q. Done. Clear with this question? See the fourth one. Cyanide on hydrolysis. You know that cyanides on hydrolysis will always fetch you carboxylic acid. Amines with CHCl3KOH. What do we call it, beta? Carbyl amine test. Just now we learned NC triple bond C. This one. Next, primary amine with NaNO2. So we just learned it. It will get alcohols and N2. N2 gas will come out. Diazonium salt will form, which will give you N2 gas. Last one is Lieberman nitroso test. We'll get R2N N double bond O. So this is yellow oily pigmentation. Correct? So check out which of them are correct. First one is carboxylic acid. Carboxylic acid can make esters with alcohol and give a fruity smell of esters. So R. Next one is a foul smelling vapor. So S. Next one is an alcohol. Alcohols will give you red coloration with the can test. So Q. And yellow product is present, which is P. Clear? See the fifth one. You are removing water out of it. So when you remove water, that is two hydrogens from here and oxygen from here, it is getting dehydrated. Dehydration is done by strong dehydrating agents, which includes P2O5 and P4O10. So answer is P first. Next. Here there is an alcoholic group here. We need to reduce it basically. Okay. So you need to reduce on all the positions here also, here also, here also, and here also. So C6H5, then here you should have alcohol, then CH2, CH2, then here also you need to have alcohol. Alcohols, I mean, anhydride or esters, cyclic esters can be reduced by lithium aluminum hydride. So answer is Q. Esters can be converted only up to aldehyde. Further reaction should not happen, means diol H. Acid chlorides converting into aldehydes. So that can be done only by H2 with palladium barium sulfate, Rosen-Mund reduction. So this is called Rosen-Mund reduction. Okay. So these are the reactions you will notice. See the sixth one. When you reduce cyanides, you'll get this as RCH2NH2. And when you react with Grignard's reagent, so first you'll get RC double bond N minus MgX plus with CH3. and thereafter on hydrolysis we'll get this as C double bond O CH3. So what are we getting? We're getting a ketone. Isocyanate on hydrolysis we'll get this as NH2 plus CO2. Clear? You'll get this as primary amine and CO2 here. Okay. And lastly, RNH2 with HNO2. So you will get this as an alcohol plus N2. Okay. So first one is also we are getting as primary amine, so which is P. Second one we are getting ketone, which is R. Third one again we are getting primary amine, which is P. And last one RNH2 we are getting alcohol, which is Q. Clear? Finished? Any doubt? Right. Let's go to the next question. Find out the reactions which involve the electron deficient nitrogen or a nitrine character during the reaction. See, first one. First one is a Beckmann's rearrangement, because oxime, this is an oxime. Oxime in proton in acidic medium will become OH2. OH2 is a good leaving group. So from here it will start moving on to nitrogen and OH2 will go away. So what do I get? I'll get PHC double bond plus with N and CH3. Thereafter, when the water attacks here, so you will get this as PH COH double bond NCH3, which will undergo tautomerism to convert into PHC double bond O NHCH3. That's how we get amides. Please try to recall the Beckmann's rearrangement once. Any doubt? Right. So notice here there is a simultaneous push of this nitrogen, I mean this group, and simultaneous removal of water molecule. So there is no nitrine forming as such here. Okay. So there is no nitrine forming here. And next we have CH3, C double bond O. And if you have a peroxy acid, can you see peroxy acid? In peroxy acid, we'll get this as oxygen insertion. And what do we call it? Baeyer-Villiger oxidation. This is Baeyer-Villiger oxidation. So it is, there is no nitrogen involved here or nitrine coming across. Next one. This is Hoffman bromamide degradation, HBD reaction. So in Hoffman bromamide degradation, we learned that first you'll get C double bond O N with N minus and Br. Now this is where the nitrine is forming. So that means if CH3 attacks here, Br will go and this group will come. So there is a nitrine character here. That means you can expect like this, right? C double bond O and N with an lone pair and empty orbital plus Br minus has formed first. So this is a nitrine form. Okay. So yes, there is a nitrine character which is developed here. Correct. Next. The same logic applies here also. This is called Schmidt reaction. This is Schmidt reaction because you'll get this as C double bond O N3. Okay. N3 structure is like this: C double bond O N with N triple bond N plus and minus. Again, you can see if you remove this, you will get a nitrine character. Then phenyl will attack here, lone pair will go here. This is Wolff rearrangement which we learned in Schmidt reaction. This is Lawson's reaction. Correct. So C double bond O, and we will get this as N3 plus N triple bond N plus and minus. Same logic. You can remove this. Methyl will go and this one. So yes, here also and here also we will see that Lawson's form. Okay. And lastly, here we have carbyl amine test. Here we will always get N triple bond C. So here there is no nitrine formation as such. Okay. And last one, this is cumene peroxide reaction. Cumene peroxide reaction. So when you do this, we will get phenol. That means this group will attach here and this will become a double bond O. So plus ketone will form. So there is no nitrine here. Okay. Now notice this one. This is also kind of a nitrine form, because imagine as if water is being removed out and you'll get a lone pair and empty orbital character. So yes, this one also is observed. So which of them will have this nitrine character? A, C, D, and E. Quickly recall the reaction names also. If you have any issue with any particular reaction, you can ask me now.
Now, could you explain the G1 again?
G. G is called cumene peroxide reaction, where oxygen-oxygen bond is very weak. Okay. So what do we get here is that when you have like this O, O and H, this is a weak bond. So what will it do? It will try to make into double bond here. So that's when the benzene will break from here and go and attach here. So you will get one as a keto form, the other one is a phenol form. Got it?
Yes.
Next one, any doubt? Chalo, seventh one, done. Eighth one. Out of the following amines, how many can be separated by Hoffman mustard oil test? See, mustard oil test is for 1 degree amine. So you can see this one, 1 degree. This is not 1 degree. This is 1 degree. This is not 1 degree. This is 1 degree. This is 1 degree. And this is not. Okay. So how many we got total? Four. Clear? We just discussed Hoffman mustard oil test. When you take with, CS2 and react in the presence of mercuric salt, you will get a compound thioisocyanate, which will smell like mustard seeds. Hmm. Examine the structure of the following compounds and find out the number which will undergo decarboxylation. So this also we did alpha and beta. Beta keto means definitely decarboxylation will take place. Now this is alpha, beta, gamma. So if you have gamma, that means you will only have dehydration happening. Okay. So here there is no decarboxylation. Now here you can see alpha and beta. Alpha, beta keto acid. Yes. So here this is alpha, beta, gamma. So no. Here it is alpha and beta. Beta diacids will also give decarboxylation. Okay, now it is alpha, beta, gamma. Now when you have it between these two, check out the structure correct way. Okay, it is better to understand how the structure is. Okay, so this is how it is. I can keep it as O and H with a double bond O. See, I've drawn the same structure here. This is first carbon, second, third, fourth, and fifth. So you can see the same thing here. 1, 2, 3, 4, and 5 here. Done. So you can see that this pi bond can take H plus. This bond can convert into a double bond here. This bond can move here. So that's how you can get here as H with double bond here plus CO2. That's how you can get decarboxylation done. Okay. So when you have a when you have a pi bond between beta and gamma, there also you'll see decarboxylation done. Here only dehydration will happen. OH and H will go away, and you'll get a cyclic, anhydride structure. So therefore, this will not give decarboxylation. Here you can see it is alpha and beta. So it is beta keto acid. Here also it is alpha and beta, beta keto acid. So from here CO2 will go. From here CO2 will go. So two CO2 will go away. Right? So in total, how many decarboxylation? Five of them. Any doubt here? It's a very, very standard JE question. You are supposed to figure out how many, decarboxylations will be happening.
So,
Yes, beta. Now, shall we go ahead? See the next one. Number of products. See, for this, if you have how many products you can get. See, again, same problem here also. At alpha position, if you have NH2, you'll get a cyclic structure. Okay, cyclic amide. So you'll get it like this. And here, if there is a double bond O with nitrogen, then here we can have double bond O with nitrogen. This is how they will be connected. Okay. And the carbon which has hydrogen here, because this is the COOH group, COOH from one molecule, COOH from the other molecule, they will both connected from the nitrogen ends here. Okay, so we will have this as NH here and NH here, and then you will have an ethyl group here and you will have an ethyl group here. Okay, clear? Now notice here there is a chiral center here as well as a chiral center here, correct? Okay, so if you have two chiral centers, right, we are expecting four stereoisomers, but there is a problem here. Four stereoisomers is because if you notice, two ethyl groups are, upwards or downwards like this. Then there is a sorry, one ethyl up and one ethyl down like this. Then there is a center of symmetry if you notice, correct? Let me write the structure again. So imagine like this, I have an ethyl coming out of the structure here and one ethyl going into the board here. So can you see from here there is a center of plane of center of symmetry here, going ethyl on this direction and going ethyl downwards here. And this side there is nitrogen, this side there is nitrogen, this side there is oxygen, this side there is oxygen. So what is it? It is a center of symmetry. Finished. So now since out of the four, right, you can see out of the four, two would be, you know, same as I mean, if one is up and down or down and up like this, they are one and the same because there is a superimposition. Hence, how many total number of stereoisomers you will get? Three. One of them is mesoform. Clear? Next one. If you have q number of products, same logic, same thing, except here instead of NH we have oxygen. Rest all is same. So here let me remove this part. So instead of this NH you have oxygen here. So you have a cyclic ester here. That's it. So again number of products being 3. Next one. If you have it at alpha and beta position, at beta position when you do decarboxylation you will get a double bond. So I can get double bond, correct, with COOH which is a trans form. I can get double bond with COOH which is a cis form. So how many products I'll get? 2. Next, last one. From here if you notice, if I remove this H and OH, so you can have ring sizes 1 2 3 4 5. So dehydration will take place. Cyclic ester will come across. So double bond O, O like this and this way. This is a cyclic ester we will get. Okay, so how many product I'll get out of this? Only one product. We'll get this as cyclic ester. Okay. So question asked is, what is the total sum of all the products? How much it is, beta? 3 plus 3 plus 2 plus 1. Total 9. Please check. Finished?
So,
Mm. Now I suggest you try the next one now because it is based on GOC. Check. Salicylic acid is like this. OH and COH. This is salicylic acid. Okay. Aspirin is O, C double bond O CH3 with COOH. This is aspirin. Carbolic acid is phenol. Alternative name for phenol. Acetic acid is CH3COOH. Succinic acid is this one, COOH and COOH. Cyclohexanone is this one. Benzene sulfamide. Benzene sulfamide. Cyclohexene is this one. Okay. So you know that when it comes to pK values here, so this one will have, acid, 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 and acid. Okay. Clear? Then phenol will also have a pK value of 10. So definitely this will also have uh, higher, acidic strength than water. Then this one is not, this one is not, this one is not. They do not have any sufficient pK value for these cases. So how many we can get? 5. Total number of carboxylic acid groups given in this case. Okay. Try it out for a minute, then I'll discuss it. So first I would have like this double bond, then double bond O, double bond O. Then on first hydrolysis, we'll get acid and acid here, correct? This is on hydrolysis. Then as you heat, because you can see this is alpha and beta keto acid. So both CO2 will go away, na beta? Both of them will go away and you will get this product. Now thereafter, you're doing ozonolysis. On ozonolysis, that too reductive oxidative ozonolysis. So you can see you can have an acid on this side as well. So therefore, you can have double bond O, double bond O, and you will get here as COOH, and here also, sorry, you will get this as COOH, and here also you can have COOH this way. Okay. Now notice from here you have 1, 2, 3, 4, 5, 6 carbons already. We cannot get a seventh. If you remove water out of it, you cannot have oxygen connection here. In that case, what would happen? Decarboxylation will take place again. So you will get this as double bond O, double bond O, and here one of the carbon dioxide will go away, generating a keto form here, like this with double bond O. So this is a final product, removing one CO2. So therefore, how many? 3. Correct. 3 moles of CO2. Clear?
so we have to find number of carboxylic acid groups.
Acha, total number of carboxylic acid group in the product. Product is 0. Okay. If the question is about how many carboxylic acids, if it is about how many number of carbon dioxide which has come out of it, so then it has to be how many? 3. Any doubt? Finished?